Hi everyone, welcome back to my YouTube channel. I'm sorry I haven't uploaded any videos in a while, as I've had a few problems regarding my good PR, the one on the left behind us, and I've also been busy with my PhD. So I'm kind of tired, and today is Sunday and I'm trying to get this video done because I think it's important to put it up on YouTube. It's a good project, so there was a lot to it. A lot to it. You'll see in this video. There's so much design, mathematics, for transformer design, and what else did I do for it? Designed it, manufactured it, and I've polished it, as you will see. And stressful times. I don't know why I do it to myself, but I'm a nut job, clearly. So this project was designed in this garage a couple of years ago. I clearly was bored. Not really, I enjoyed doing it. It was one of the first projects it will be one of the first projects on this channel that has my signature right across it, as you will see what I'm talking about there in a minute. The fan has just come on this. So this system was designed to be compact and lightweight for all users, whilst allowing for the independence of awkward tasks that can arise using a standard single-phase spot welder. Users are required to clamp the metal by squeezing their hands using an ordinary single-phase spot welder, and the transformer is also in the unit, in the clamp. This is different, this is separated. It was an experiment to see how it would work. It does work very well. There's obviously going to be a bit of losses here in these cables between the devices, and so the greater difficulties with hand function, the greater the impairment in the skills using such devices, such as these heavy transformer devices that you could buy off the internet, eBay, and they're £1,000 roughly, maybe a wee bit cheaper. But they're great difficulty using them because they're quite heavy and for some people, and you need somebody with limited hand strength can find it hard to clamp them. So I went away and experimented with microwave transformers, as a lot of people have done in the past. However, there were issues here as I will discuss. The project is an experiment to keep the bulky, heavy transformer, the high current transformer, away from the clamp itself. This is mainly to eliminate 5 to 10 kilograms. I'm not actually sure how much it is because I don't have one. I don't have a spot welder. I just bought this one for the purpose that I needed it for. That guy there. It's still not finished because I'm doing stuff like this. But I don't mind. I don't mind no more. So it was an experiment. I did an experiment with cables, materials, these cables, the dimensions of the cables, the length of the cable, and all that. I had to experiment with the whole lot. I also made the clamp device pneumatic, where the pressure could be adjusted if needed. So you can adjust the pressure if needed of the clamping device itself. Something you could do with your hand too in an ordinary device. The system was developed mainly for spot welding in awkward positions of cars, such as wheel arches. That's what I built this one as a C-clamp sort of a design, so it gets in the awkward areas. I also made this design so that you can make new arms in the future if need be, different shapes and sizes. But in the meantime, this is all I made, just to experiment with this project. I don't know if I'm ever going to use this project. I think it's maybe just something I'm going to set away because of how much effort I put into it, how many hours and stuff like that, a lot of time. I don't know how many hours I put in it, but I'd say there's a good 1,000. That's coming from polishing and all too, and designing, and maybe more, I don't know. I never kept count, but I know I was tired a lot of late nights. Lying out in the grass, polishing with sandpaper, and I'm a nut job really. So I have a lot to talk about, and I have electrical, mechanical, pneumatics, mathematical calculations for the transformer before I even go on to demo the project, the spot welder welding. The project consists of a pneumatic clamp with a selected pneumatic piston with the correct stroke, the correct pressure required for the pinch point and the clamp pressure. The system has a customized, specially designed high current transformer, as I says, that is housed in this handcrafted box. I'm going to take this enclosure, I'm going to take the whole lot in bits. So I'm going to take the enclosures off the spot welder and the transformer. I'm just going to show you inside it. The system transformer is very high current. There are many components on the low voltage side, controls such as for pulse, on delay, off delay, hold time, and all that stuff that's situated around spot welding. Approximately 90% of these components are cut and shaped using little machines. So I've handcrafted them using hand tools, grinders and files and stuff like that. Each device was carefully designed using SolidWorks, where the transformer enclosure was designed around the custom transformer. So the transformer was designed first, and the clamping device. The clamping device just needed to be compact and with the right pressure, like pneumatic cylinder, and the enclosure just needed to be compact around the transformer to protect it. But I went overboard, as I always do with every one of my projects. And many people have chopped high voltage transformers that power the magnetron of microwave devices in the past for DIY welders. I have done this in the past too. I've done this probably 15 years ago, but it tends to be ineffective and not very efficient for such a project like this, considering the distance between the transformer and the clamp and the electrodes. I went better again and designed my own high current transformer with a bigger core, so it has a deep core, and it's really good. This transfers much more power without getting saturated and heating up as a microwave transformer does. And I have experimented with them. There's a lot of losses, and the core heats up very fast, and so that's why I went and designed my own transformer. And you will see it's very powerful, and you can hear this thing going here. There's core cooling. There's a stat, the temperature probe in the core, and it's now reading 16 degrees on the top of this unit. As I say, I'm going to go into detail. I'm going to take all these projects in bits. I'm going to take the cover, I'm going to show you the transformer. I'm also going to step through it on SolidWorks. So the way the transformer core is designed has a major impact on how the manufacturing and the final product welder has turned out. It is crucial to have a strong transformer core design. The high current cables, so these high current cables is 95mm square. They're quite heavy, but you need them, and this to keep the voltage down, keep the resistance level down. So when you see, keep the resistance down. I did have, what was it, the size was it? 72mm squared or something like that, but now it's up to 95mm squared. As you can see, it's not that bad. Like, I didn't think they were going to be as heavy, but you need them, and if the heavy cables wasn't on it, there'd be a lot of wouldn't be as powerful and be less efficient. So this is these cables is to ensure that the secondary winding resistance is kept to a minimum. The high current cables length. So the length of these cables is, I think it's 1200 or maybe 1400 millimeters between the transformer and the clamping device. That is important. If that length's too long, the resistance needs to be kept as low as possible. So Firstly, I'm going to, during the rest of this video, I'm going to start by giving an overview of the system in front of us. So I'm going to do a video now in a minute. I'm going to strip this unit, and I'm going to tell you how it all works. I'm going to run through the design of the project on SolidWorks, starting with the clamp. Then I'm going to do mathematical equations on the transformer, as the transformer came second. Then I'm going to do SolidWorks, starting with the next with the enclosure, sorry. So the enclosure next, and after this I'll move on to the base of the enclosure and stuff like that. And I'm just going to show you the pneumatics and the controls and the electrical connections and the electronics circuitry and what microcontrollers inside it, how the core cooling works, where the transformer is positioned, and why I've designed the stack to be such a length. So the transformer inside this enclosure takes up the full length of the box. I'm now going to do a wee short demo, but with no metal. I'm going to have the electrodes spaced apart further than they should be. But at the end of when I have finished talking about the design on the videos, there will be, at the end of this video there's going to be about, I think there's about 100 to 150 photos. I'm not sure how many there is, but there's a lot of the detail went into in building this machine, the system. So I'm going to do demos of this system welding, and at the end, when I've finished talking the design in the video, obviously I'm not going to put on, I don't have the videos of making this because it takes up too much time. As you can see, for me to sit and take videos of building this device, it would have took months. So here you go. Now this is it up close. I'm going to just show you here now first. I'm going to show you the pneumatic piston shooting out. The transformer won't kick in because there's an off delay for 1 second. I think I have it set up for 1 second. So, alright, so there's the valve clicking when I push the button. It doesn't latch for 1 second, so the transformer doesn't kick in. Let me show you, I'll bring these around the front. So here, I'll bring the box closer. So here, look, there's a button here with my right thumb. This machine was designed around a right-handed person, obviously me. So I've designed this enclosure, this side for my thumb. It doesn't do nothing until it latches over. There's an SY control cable here, the 2 high current cables is here, and the clamping device is here. It won't do nothing now when I push the button because there's no air going on there from a compressor. I'm going to plug it in now to sample it, just to show you. Hold on. Get this hose. So here we go. Pneumatic air now into the device. I'm going to bring the transformer up again closer to show you the video. Okay, so here we go now. So the clamp design going out. Doesn't latch over. This is not going to weld. There's going to be no sparks and stuff flying off it, obviously, because I have a gap in between. I have this electrode took out further than it should be using this Allen key. See the Allen key at the top there? So there's about a 5mm gap so that I don't cause any sparking of the electrodes. Them electrodes at the minute are too pointy. They need shaped and they more in their ball. I have to do like it because I noticed that it wouldn't weld as good when the points was like that. So 90% of this, these parts on this whole project is specifically made, handcrafted, apart from this pneumatic cylinder and this valve. Everything else, when you see this handle is fabricated, it's not machined. It's 3 bits of plate welded together, it's anodized, but we're going to do more detail in a wee minute. I'm going to show you this latching over now. So here we go. Hold it for 1 second and this unit here will be engaged, it will be powered up. This will latch, the current will be going through, it won't pass through because they're not touching. The secondary winding coil is not complete. There's a wee 5mm gap. So here we go. I'll do it in the video closer again. So there's obviously no spark in there because there's a gap between the electrodes, just to show you it working. That beeping noise is to say that the transformer is to say that, sorry about the video, because I'm trying to aim the camera down to get this project in, as well as standing in front of the video. So that beeping noise is saying that the transformer is ignited or powered up, the primary winding. I'm now going to go into detail. I'm going to take these covers off and I'm going to show you inside and the workings of it. And I will then follow on. This video is going to be very long by the looks of it. Okay, so I've brought the welder outside now, the system outside, to show you it in the daylight. I'm going to take it back in the garage to talk about it because there's too much traffic out here passing. This is the handheld device. This is the two clamping cables. And this is the enclosure that is built. And that's a supply. Just 230 volts, 13 amp. This is the enclosure. So you have a cooling fan at one side and another cooling fan on one side. They're both going opposite directions, so one's sucking and one's blowing. You have a main power switch with LED light on it. Or sorry, it's not LED, it's just a wee bulb. You have a control, 2 button controls for the timer, for the transformer, so you can set it up to pulse. And you can also set on, you can set on delay, off delays and all that, off the transformer itself. So as you can see, the box has been specially designed to be different. Could have made a square box, but I made a box that has 20mm radius, a 40mm radius, and that wasn't easy now filling in these corners, but I will show you how I done that. As there's a 40mm radius here, 20mm and 20mm, it's going to be quite difficult. You're going to be left with a hole here. So this box is fabricated up in one piece, all apart from 4 corners set in. The box is purged of argon fruit, so it's basically purged just the same way dairy pipes is purged. It is sanded through so many different stages, then polished up the mirror using different grades of soap, bar polish, black polish, black, I think it's black's a starting polish compound, then it was brown, green, then pink, so the wee final polish, but the green is the main, using different types of polishing wheels too, obviously. 8-inch wheels on a Metabo bench grinder. So the traffic is going up and down the road here and I'm trying to work around the noise. So this clamp design is built out of 3 pieces of metal. If you look closely here, it's TIG welded. There's a piece of 6mm machine aluminium, 6mm machine aluminium on the outside. There's a gap in the middle, but I will go through it in more detail how it's not just welded. There's a ring. There's a ring set in between the 2 pieces of aluminium the whole way around to keep it from pulling when I was welding it. So this piece here looks like one solid piece, but it's actually 3 bits of plate. These curves on the edge of this welder, you can see it in detail here. That's why I brought it outside. So you can see there's a nice curvature to it. There's no indents. You see that dark and the lightness there, it's anodized and it's actually a nice effect. You can see the welding below it. If you look closely, so you can see it's not machined. This is the valve side of it. So this is the valve side of it. It's just my sweaty hands. That's the platform that the pneumatic cylinder sits on. You can see a weld there. That wee enclosure was also made out of 3 or 4 pieces. but I tried to make it as close to one piece as I could. But as you can see, there's lots of corners and stuff on it around the switch. There's another control in there, so there's a control in this to control the pneumatic cylinder. Adjustable control. It's a microcontroller board. There's also another control in this, as I was talking about a minute ago. 2 switches. You can adjust settings in it. So basically, it's a clock pulse timer. I could have used an Arduino or something, but at that specific time I didn't. I wanted to keep it more simpler with no programming, but I can actually program them boards using the buttons there. So there's people out the road there now. And so this pneumatic cylinder is specifically designed around the clamping force. The stroke is selected to be, I think it's 40 or 50, it says there. Sorry, it's 50 stroke, 50 bore, 30 stroke. So the 50 bore is to do with how much force it gives out. There's also a control valve there for regulating the pressure. This guard is specifically handcrafted too. One day I took to build the guard and stain powder coat. These brass blocks is also made to hold the electrodes. There's a wee grub screw here. The clamping cables is bolted directly onto them. Now there's also 2 wee buttons in this to control the module in there. This SY cable is control cable, so there's low voltage. There's never a high voltage up here. The voltage coming from a secondary winding, and then the transformer I bought is only 1.7 volts. I have tested this. I will demonstrate that later on. This SY cable has only got control signals in it, such as 12 volts, 0 volts, and that's it. Nothing else. To power that solenoid that controls the pneumatic cylinder. Sorry, the pneumatic air goes onto this male valve here. There's 2 exhaust blow-offs here. That noise dampeners. There's like what do you call them? Mufflers. I'm sure there's a technical name for it, but I don't remember. And I think it's polyurethane pipes. I think I had nylon pipes at the start, and they were too rigid. That there valve is directly bolted on to the actual plates. You can see there it's 3 plates there now. When you're looking there, look. So see the arm going up. That stainless arm is 304 grade. I think this is 316 grade. I think it's 304 because it's a wee bit harder. Them air's clamped with them white cables is clamped. This yellow guard, as I says, it took a day to make. Was made out of 4-inch pipe, and I will go through all that in steps and later. The holes is bored just for to remove weight, and the guards to keep you from putting your fingers in the air. And see when the valve comes back down after doing its full stroke, it could crush your finger. Or it happened to me before when I used to work out in industry. There's a lot going on in behind this guard too. You have an insulator that breaks the winding. So if that insulator wasn't there, the secondary winding will be already linked together, if that makes sense, through the spot welder. So there's an insulator in there, and it's a piece of nylon block, so it needs to be hard and solid. I'm going to take it apart in parts later on and show you how it's done. The bolts, there's 2 bolts goes up and holds the brass block on top of the nylon block. There's heat, as you can see there if I zoom in. Do you see the wee bit of fiberglass board? That's to keep the bolts from heating the nylon. There's also a fiberglass board, copper fiberglass board beneath this block. You can see it there, sort of. In between the guard. Where is it? It's hard to see. Let me see if I can pull it out here. I couldn't get it out, so I forgot to say too. There's an insulator block in here, and there's a fiberglass copper plate between that and the brass block. The brass block end is held by 2 stainless steel bolts. So if you guys to put a multimeter between the body of this and this top or this lower brass block, there'd be no continuity between them because it's insulator on here. The bolts there's a metal washer made between the nylon block that supports the nylon the pressure that the block is squeezed to the nylon, if that makes sense. The piston is then connected to the nylon block. It's a wee bit tricky without taking it apart and showing you. This guard also supports the block from turning, so it keeps these electrodes in the same position all times. So it's like a guide at the back of it. The nylon block always rests against the back of this guide. This guide is guide is connected directly on top of the pneumatic cylinder here at this point. So it's, in my opinion, it's quite well designed, you know. As I was speaking about earlier on, there's a bit of plate in between the two plates going right round the body of this. This router with a wood router, just an ordinary wood router for a kitchen worktop. I think it's a 10mm radius. I think it's quite small. That's a stainless steel switch to match the stainless steel cover. I'm going to take it apart and talk about it in more detail, but I think it deserves a good video. So I need to mention is when I'm holding this device, I'm actually connected to the secondary winding of the transformer, but that's standard practice within even ordinary spot welders. The voltage is so low, but at the same time I'm not touching the lower end of the coil. That's only 1.7 volts between these two electrodes. Forgot to mention that this electrode's held by two stainless screws there. That brass block is also supported by, you can see a wee design plate at the top of it. So when the electrode pushes up, it's so designed to be so tight. So you see, so when the pressure pushes up in this, it's not just dependent on the bolts they hold it. This wee plate that's angled down is resting on top of the block. This block is as tight as possible in this position, and it's also designed to be, pinching point is to be really close to this point so you can get into tight spaces. You know, so say if there's a bit of metal coming on here like this, you know, you can get in tight. This is angled down, so there's a lot of thought that's went into this. This arm can be changed in future for different shapes. So say if I wanted to make an arm that goes out here a wee bit, it would obviously need to be rigid and designed well. This unit, as I said before, it's designed to be compact. So this valve here controls the pressure from the out on the piston. I never have to touch that, right enough. Never have to touch it. These electrodes should be round, not pointed. If they're round, it means there's a better chance of connection always on the steel. If they're pointed, it means they can run off, and you know, it's hard to explain that. So if there's two balls coming down parallel to each other, two rods, a radius and end it, there's a chance that they'll always be hitting on that radius, but with points, the points can be off. So that's a problem here. So I'm gonna take these back to balls, to round radiuses. If that makes sense, I think it does. Makes sense to me anyway. Okay, so I'm gonna take it apart, maybe bits of it apart, and show you it closer. And there's a lot to it. Okay, so I keep saying I'm going to take the covers off the system, the enclosures, to see what's underneath them, but I think it's good that I show these models of both the transformer enclosure, the clamp design, or clamp enclosure too, underneath it. But I'm just going to show you the three models of the enclosure first, then the clamp design, and then I will look into the transformer itself. So here it goes. So I'm going to make this cover transparent to see through it, if I remember how to do it. Okay, so there we go. So I'm going to start by giving a wee discussion and try and keep everything in the center of the screen, because I have to rotate it as we go. So here we have let me see if I get this centered. Here we have the main switch for the income supply. Basically it switches the live off and on, and the power is supplied through this gland, 3-core cable, live, neutral and earth. The full body is earthed. The shielded cable going up to the clamp design is also earthed, and also supplies earth to the clamp design itself, so it's all protected. Where do we go from here? Right, okay, we'll start with the cooling. So the fan, or the transformer, is cooled using 2 fans. They are small fans at approximately 60 70 millimeters. I think it's 60. One is drawing air in the way, and the other is taking air out. So cold air in, hot air out. This is controlled using a digital stat up here in the top. It is bolted to the enclosure itself. There's a probe, or a stat, temperature probe, running to the stat even, and it is embedded within the core. It's just sort of like stuck in there, and you can set the when you want the cooling fans to kick in, like say 20 degrees or 25 degrees. You also can set how long you want it to stay on from its initial starting point. Say 5 degrees below it's where it kicked in, so it cools down further. There are settings that can be controlled using them 3 buttons. Let me see if I can get through the hole here. I'll zoom in. So here we have the 3 buttons for the digital stat. There's a display there, but these buttons control, or these be like sort of 3mm shafts, control the buttons on the PCB board. The board is mounted to the cover using, let me see, these wee bolts, which they are transparent at the minute. Let me see if I pull it out. There's bolts here, and then there's nylon. Let's see through the hole here. There's nylon rods, or nylon extruded bits. My threads on it and nuts. I'm just gonna make this clear again. So there's nuts and washers holding the board. It's important that this board is isolated away from the cover itself, as you don't want to shorten the wee board out. Where else do we go now? So here we have a clock timer. It controls the transformer, the pulsing, on delay, off delay, and this controls a relay, 10 amp relay, which controls the primary winding of the transformer. We're going to explode this here now, and we're going to look at it in more detail. These 2 glands is for the high current cables. The high current cables come in from the clamp and are bolted directly to the secondary winding, which is 1 turn of the transformer. This other gland here is for the 7-core SY cable running to the clamp, which is control wires. So it's basically just low voltage, 12 volt and 0 volts, and also an earth wire and a shielded ground. Let me see, we're going to explode it here now. So let me see now. If we explode this somehow, if I remember how to. Right, there we go. So we're going to talk about it in a wee bit more detail now. So we can try and keep it in view because there's so much to it. Right, so at the bottom here we have rubber feet, 4 rubber feet that are bolted using 4 dome screws. There's nuts and washers at the top, so they bolt directly to the base. These flat plates with holes in it here are tapped to, I think it's M5 threads. They are welded, they are placed on these holes, these cutouts, and they are welded along here. This is to mount or bolt the top cover up here onto this when the transformer is in it. The transformer lane, let's see if I try and keep this in view. The transformer is clamped using these 4 rods, which are 5mm threaded bar. They don't have no cosmetic threads on it, but they should. Whatever happened. There's nuts and washers at both ends, and there's all the E&I laminated strips are bolted together or clamped together tight. These wee brackets, L brackets with 5mm threads are welded on to this. Obviously the brackets are not welded to the transformer, but I'm saying this stud, these threads is welded into the bracket, and the bracket is directly bolted onto these holes on the base. The threaded bar here runs directly through the whole these wee L brackets, and the nuts and the washers are held in place, hold the whole lot in place. And the transformer is placed on the base, and these nuts and washers then are then used to fix the transformer tight. Okay, so I'm just going to talk about everything else in a bit more detail now. There's as a transformer is quite heavy. There's a handle with a nut and the nut is, I've actually took a nut out of there just to show you what's on behind. But there's a nut on that nut is usually placed on behind here with a washer. This is TIG welded around here. This is all TIG welded, as you see, you will see in the real model, practical model. What else is on here? Right, okay, so here these circuit boards is held using these wee nylon extrudes, boss extrudes, or what do you see? And there's guides. These guides, I'm going to make this box. These guides here is used to they are TIG welded first onto the box itself, and the 3mm shafts with washers tacked on it are used to control the buttons here, and they can't get out because they're on the side, they're on behind, they're in front of the PCB board. So the PCB board is isolated away from the metal itself using these nylon boss. They're like nylon shafts or boss extrudes. And there are male thread here and female thread here. The female thread bolts directly onto. Let's see if I can get back inside this. The female thread bolts directly onto here, screws onto this even, and that's about it. I could go into more detail, but that wee transparent glass is glued directly onto here. I could show you inside of this when I'm at it. So that wee transparent glass is just epoxy glue down here. There's also more cap bolts. They're only about 5mm long, tack welded onto here with a TIG, or spot welded you could say. And there's one here very close to the edge. And these is also 3mm tube with 5mm on the outside, and the wee bars slide up and down to control the buttons. That's dome head and washers for the handle. These holes is cut using a laser machine. The box was initially designed a 3D model, then I flattened it. I will show you that in more detail now. Is there anything else I've missed? I don't think so. There's a lot of parts involved in it, so there is, and as you can see. But the clamp's worse. The clamp has more parts, but we're going to just flatten this box here now and show you what it looks like when it's flat and how I fill in these corners. So before I flatten this, I'm going to just describe what I'm talking about. So this box was initially designed to be round, not square. A square box would be 100 times easier than this. So this box is made in one piece of stainless. So there's one weld down here and one weld down here. right round, 4 welds, and also they are welded here. But there's also a cap needs to be placed in this hole. However, this is not easy. So what I done is I've cut a tow bar off a car, and I have placed a bit of metal over it, and I have pushed the metal using like a homemade press. Push the metal over the tow bar to create like a dome shaped bit of stainless. Then these bits of stainless was cut out to fit in here. The box was then purged, TIG welded, so there was argon, all the oxygen was pushed out of the box. The lid was put on it, or the base was put on it, and all these holes was taped up, and the box was purged. The reason it was purged is because if it wasn't purged and I was just keep sanding the weld back, I would have ended up hitting, holes. So purged means is it's weld right through to the other side, and the other side is welded. So I'm going to flatten this box now, and I'm going to show you what it looks like when it's flat. Okay, so if I remember how to do this correctly. Okay, try and keep it in view too when I'm doing it. So flat pattern, so that's flat pattern there now, so I'm going to try and get a top view of it. Okay, so there we go. That is the top view. These holes is for the cooling fan, these holes is for the wee digital circuit for controlling the transformer, the microcontroller. The 2 glands, the SY cable, the handle, and it was cut out in the laser machine, so obviously I used a machine to do that. But see, now we're left with these holes. The problem is this box has a 20mm radius here and a 20mm radius there and a 40mm radius there, I think it is. Or it's a 10mm radius there and a 20mm radius, I think. So there's about 20 to 30 folds between that point and that point. And there's also, at this end there's far more, there's about 50 folds between this point and this point to give you that big radius. If this was a square box, it would be basically just one fold, but it would not look as nice. So I went overboard, as you can see. The corners was, you'll see pictures in the end up of me doing the work with the press, or the wee bit of press steel over a tow hitch of a car, and I didn't cut it off my own car anyway, but I just found, I think it was a scrapyard I might have took it from. And the top part of the tool that I used was a bit of pipe at about 3 inch, and I pushed the stainless over it with no heat, and it actually worked out quite well. So what you will see in the pictures at the end of the video. So we're going to go back into the model here before we move on to the clamp. What do you see now? If we can find it again. That is not the model, so there we go. So we're going to move on to the clamp now, but that is basically the design of the enclosure. There was a lot to it, as you can see, and it wasn't that easy. Like, there's a lot. The transformer, I'm going to talk about that at the end. The transformer was a lot of mathematical equations required for design, and the bobbin was custom designed. You can't buy a bobbin of that size over the counter for a core of that size. It's 133mm long. I'll make this box see through again. It actually looks better. So it does. It'd be nice if I got a box to get in real life, but stainless mirror is grand. That caused me enough heartache. So we're going to move on to the clamp now, and the clamp's will be a bit more complex than this, more moving parts, more mechanical. And I hope you enjoy it. I know the video is long, very long, but I do not have the time to make hundreds of videos off this project, so I'm trying to put it all in one. So we'll move on to the clamp now. Okay. So here is the clamping device. As we now know, we have seen it in the real world. I'm going to start talking about the clamp design itself here, the blue part, which is anodized. It is anodized a nice like a titanium blue. It's actually a darker blue than this, but we're going to talk about the actual design now. where I started. So I started building this clamp design, working off hand design first, or hand shapes and sizes. So as this hand held clamp is not machined. It is three bits of it is fabricated out of 6mm aluminium. There's 3 bits. There's one layer in the middle, layer on the outside, and a layer on the other side. And there's a left and right because the holes at both sides are different, as you can see. This side has an indent on here. The middle layer continues the whole way round, right round the bottom, right round, and up the top. We'll get it back on view here, as you see. So, the clamp design was designed. I first laid my hand out on a piece of paper and I measured between my fingers, roughly about, I think it was about 25mm between center of each finger. So at this point, to here, to here, and to the baby finger was about 25mm between them, and that's for a large hand. But also this design can also it could be used for any hand sizes, but I just made it round my hand size for large size. Also, this distance here, this was at the very start flat, straight down here. Didn't have this wee curve in it. This wee curve gives a better feel, a better gripping. You can grip the device better. As it's a wee bit thicker and broader, it fits the hand better. As it gets narrower, it gets broader in the middle to suit the hand, and narrower on the outside. This bar at the front here, or this structure here, the whole way down the front of your fingers, is actually protection for safety measures. It's this, say if the pneumatic spot welder piston shot out and it wasn't positioned right, or it was sitting off at an angle like this against the metal, and the force of the piston shot out, the other way, and ricocheted the pneumatic spot welder that way. This bar, or 3 bits of plate, aluminium, it's all welded together and shaped, is to protect your fingers. So if there was a bit of metal here, this here would stop your fingers from getting banged or even chopped off. I wouldn't say chopped off, like we're getting bruised or crushed, but it actually looks nice too. It looks well. So initially at the very start, this was cut off here, straight. It had a wee curve in it. It looked actually mine now. It made it went up in a wee curve like this, and down here was just basically rounded with like a 40mm diameter. Think of visualize a circle there, and it actually looks far better. So we're going to talk about it in more detail now. Then we will explode it. The clamp design has a pneumatic piston that shoots out a contraption here that has lots of plates within it, as acting as heat barriers. And there's also this yellow guard, which this yellow guard actually took 1 day. It took 8 hours to make it, hand make it. Each hole is individually bored, and it is powder coated yellow, and it not only acts as a guard, but it acts as a guide for this nylon block. This C-clamp design can be changed in future if need be. We're using these 2 bolts here. This enclosure cover is made out of 316 polished stainless, and there's also a pneumatic cylinder here that controls the piston itself. So I'm now going to explode it and talk about it in more detail and see how it goes from there. Before we explode it, we're going to give a wee brief talk about the pneumatics and show you how actually the 2 electrodes approach each other when the piston shoots them out. So first of all, when you push this button, the pneumatic piston shoots out and touches the electrode. This can be adjusted, but these electrodes can be adjusted using the scrub screws. There's actually none on it. There should have been scrub screws in it, but they have vanished. I'm going to have to add them again. The nylon block pushes the brass block and the electrodes together. The electrodes need adjusted in this model. They shouldn't be coming together that close. but this one just needs to move back a wee bit, but I have it locked. And when the electrodes come out, so I'll start from the beginning. This switch starts this timer, and the timer doesn't latch for 1 second, and the piston comes out and in like this. When you push the button to allow you to line the device up where you're looking to weld, the device won't weld when the contacts touch each other. They still won't weld if you keep releasing the trigger within 1 second. You get used to it. It's actually quite a long time, 1 second, when you're doing this. And the device doesn't weld until you hold the button longer than 1 second. So when you finally meet your welding point position where you want to weld, you push the button for longer than 1 second and let go, or even you hold it in if you want, but you can let go and the device will do its cycle. So then the signal is sent to this here, this pneumatic cylinder. This is held on for until this device in here delatches or counts down. The timer counts down. You can set it using these two wee buttons here. You can push them in. You can show you. Go down now. Two of them do different things. You can set on cycle, off cycles, and hold times and stuff like that using that timer. So air then is a pneumatic air is passed in through this coupling, Euro coupling here, and this is using a flexi hose off the roof I use in the garage. Air is passed into the pneumatic cylinder here. There should be polyurethane pipes on here, but there's not. Polyurethane pipes is selected because nylon's too rigid because they go around these corners. They're very sharp. Everything's very complex. So when the air is passed in, this here's high or alerted here. The solenoid, it's open. The bar moves in here, inside here, using a solenoid. The valve opens. Air is past the cylinder. The piston shoots out, and the air is exhaust through one of these ports. These wee brass things is actually silencers, so it stops the hissing noise. It dampens it away down, giving it a nice noise. Also, the air then is passed in when the valve is de-energized. The air is passed the other way, and the piston returns using the same force back. This is why this guards here. We'll talk about it in a wee minute when we explode it more. Just keep your fingers between nuts. So you can't put your fingers through this hole here. This guard also has another main use, is to keep this block centralized, because that electrode is not center with the piston. As you can see, it's a wee bit off. It's just due to the design itself. So when the air is passed in the piston is shot out. Then the signal is sent down here to the transformer enclosure through this SY cable. So a 12 volts is passed from this clock cycle timer down to the enclosure, but the transformer does not start because there's like an off delay before it holds the transformer from starting for, I think it's milliseconds, or maybe 500 milliseconds. I'm not sure. It's not very long anyway. And then when after that time is complete, the two high current cables current is passed through from the custom transformer. Very high current. We will test it at the end with a clamp meter and show you the current. We're going to explode this now, clamp design, and see the inner parts, the buttons, and how everything's put together, especially this up around this area where there's glass fiber boards acting as heat barriers, for instance, and there's a wee bit compact in here, so we're going to break it down. Okay, so we're going to explode this here now and see what it looks like. So here we go. There's a lot of components in this, probably more than the transformer enclosure. So we're going to start working at the bottom. No, we'll work at the top and work our way down. Okay, so this C-clamp design is bolted onto here using 2 bolts and nuts. We didn't tap the aluminium because aluminium tends to wear when you put a harder material against it over time. Replacing arms, if ever need to replace the arms, I use nuts and bolts instead. these nuts is actually on the actual item itself. It is cap dome nuts, so they're much more fancier looking and no sharp edges and stuff. So we'll work our way down from the top here. Okay, so these are 6mm M6 by 10mm bolts. Hold this brass block onto this arm. This arm is designed to be complex and very tight, like very narrow here to top to fit into complex areas. This brass block doesn't just depend on these bolts to hold it when the pressure is pushed against it. This 6mm overhang here is designed to rest tight here, so any force applied hits this outer tip rather than straining the bolts. It works really well. These electrodes that's held on these brass blocks that are handcrafted using grub screws, 6mm grub screws. There's also a brass block down here that is sitting on a bit of glass fibre board. This glass fibre board acts as a heat barrier to protect the nylon block, which is only rated about I think it's 80 degrees temperature I think it can stick before it starts melting. So this just in case this brass block heats up to a high temperature, this glass fibre board acts as a heat barrier here. It stops the heat melting the block. The bolt that holds this nylon block to the pneumatic cylinder is recessed or counterbored into the block. So the head of the bolt sits way down in here and 1mm below the surface area, top area. This other glass fibre board at the bottom is also to protect the heat travelling down the bolts coming from the brass block. These two M6 bolts here, as they prevent the heat coming down the bolts and back up and melting the block. So this glass fibre board acts as a barrier. This other wee plate that mimics the exact same perimeter of it is a washer just, but it's a stainless steel, and then there's two other washers on top of it. Then there's two 35mm bolts, I think a 35 or 30mm bolts that hold this all together. These bolts go right up through the block, the nylon block, and all these wee washers, right up through this glass fibre board and into this brass block. So this brass block is tapped here and it is held tight. So when the pneumatic piston pushes the nylon block, all these wee components move together with the electrode. The only thing is, there's no continuity between this arm and this brass block, or there's no continuity between this brass block and this brass block until the transformer is ignited or powered up. Then there's a complete circuit of a secondary winding. So it is important, we'll talk about this more within the transformer design, but it is important for these cables to be of low resistance and keep the voltage levels down low, and also to reduce any losses of the cables, copper losses. So that's the reason 95mm squared cable was selected. So we'll go down to the bottom here. This yellow guard not only acts as a guard for the fingers, as I described a minute ago, it usually sits down here. It acts as a guide for this nylon block. This nylon block runs very tightly against the back of this guard. This guard at the back is actually thicker than the front here. It's 2mm at the back and 1.5mm around the sides. This wee triangle piece of aluminium in here, this is TIG welded in, which is now powder coated. It acts as just a right angle support for this because there's a bit of pressure against this. For instance, if this device pneumatic piston has no air in it or no air connected here to this coupling, I cannot move this nylon block in and out with my hand. But if this guard wasn't on, this nylon block comes in and out easy, so it's good. So the two M8 bolts here at the back of the guard are to mount it onto the piston itself. Two washers also are used. This bracket, as I said, is 2mm thick, so it's much stronger than the guard itself. The front of the guard is designed as a guide here at the back. It works really well. I will show it in demonstration later. The piston itself, I might have said this already, is mounted to this plate using 4 M8 bolts. I think they're 15mm long. No washers are required. This plate is welded here, and it is also welded at the back at these 2 points for some more extra strength. The pneumatic piston itself is bolted using 2 M3 bolts. I think they're 30 mil long, and the aluminium, this plate is tapped here and here. This round bit cut out of this aluminium side here, this aluminium face, is to allow for this coupling, Euro coupling. So when I put the fitting in from the airline, it fits in and it doesn't hit this. If this wasn't here, it would hit. So it's very complex. Where do we go now? So we'll talk about this side a wee bit more. So these brackets here are for the mounting of this wee small enclosure. This wee enclosure. So there's 4 of them, and these bolts here. Sorry, I'm a wee bit out of view here. These bolts here screw into here in the tapped hole. This bracket screws into the tapped hole of the plate using 4 mil. I think it's, no, sorry, these are 5 mil and these ones is 4 mil. So these is 4 mil dome head screws. Goes through this hole into this bracket to bring it all together. And these nylon or wee boss extrudes here are male thread at both sides. They screw directly into the side of the spot welder, and they act as a barrier or insulator to isolate the PCB board away from the side of the handle, keep it from shorting out. The PCB board is attached using a nut and a washer. Here, this nut's actually nylon, it should be black. This polycarbonate screen is glued with epoxy glue onto the stainless enclosure here. Also, there's these wee buttons that control the PCB board. They move in and out, and they rest 1/10 thou or 1/4 of a mil approximately away from this button. They slide in and out the wee guides that are customly made up, same as the transformer enclosure. So it's about a 3 mil inside tube and 5 mil outside. And they are tacked in 3 places, or 3 or 4 places. As minimal, tacked as little as possible to keep you from distorting this face because it's polished in the mirror. This switch and this gland, this gland is for the control cable of the transformer, and it's 7-core SY cable that runs out of this. It's quite flexible. This switch is the starting switch, as I've already talked about. It is mounted here at the back using a nut, and this gland is also mounted at the back using a nut. I'm now going to talk about this wee small enclosure more detail. I think I've covered everything else. Yeah, that arm can be changed for different shapes in future if needed, but at the minute this is just a prototype to see how it goes. Oh yeah, there should be polyurethane pipe around these, as I already says. These hex nibbles, they're 6 mil push fit, so a bit of polyurethane pipe just pushes straight into them. There's only 2 bits of airline on it. Where do we go now? This cover. Okay, so this cover's a wee bit. We're going to flatten this. We're going to open the part up and we're going to look at it in more detail. Because this cover actually has a wee bit set into it. There's 1 piece there, 2 piece here, 3 piece here. So this cover's made out of 4 pieces. 1, 2, 3, 4. Yeah. So yeah, you can't actually have this full because this one, gets in its way. So we're going to go on it now and open it and show you in more detail. Okay, so we're going to flatten this cover here now and see what it looks like. Show you what it looks like. Okay, so open this part. We'll turn it around, face view. Okay, flatten this now. So this is what this cover looks like after it's flattened, or before I folded it even, and there was 4 folds in it. However, you can't obviously have a wee piece of metal here because this one is in its way. So I had to put a wee bit in here, and you can't obviously put a fold on a curve. So I had to weld a bit in here, and also this curve I weld a bit in here. This hole is for the cable gland. The hole for the switch is a bit of metal that needs to be set in. These 4 M5 holes is for the mounting holes of the enclosure. These 2 holes is for the 3mm shaft that, or the wee extruded shaft that control the switch or the timer to set the on time and off time of the actual pneumatic piston itself. So we'll unflatten this here now and open the model up again before we move on to the transformer. There we go. So there's the wee pieces here. So there's this wee bit with the switches here is TIG welded down here, and it is sanded and polished. This cover is not purged like the enclosure because it's not required, because you're working off the edges. There's much more. You're not gonna, when I weld, this is gonna be like a good fillet weld. The enclosure is different. You don't want to be sanding through the holes at the corners of the enclosure where I set the pieces in. So it's a bit hard to explain that, but this is welded down here with the TIG, and down here and down this face, and also down here along this face. This is open. This is against the blue plate where the pneumatic piston sits on. This is polycarbonate, it's meant to be up close to it. This is also welded down here and down this side. This is all sanded and polished up to mar, as it's a prototype project and I wanted it to look special. So that's it. I think I've covered everything. Hopefully I haven't missed nothing. It's very complex, there's a lot in it for what it is. And this part here took a wee bit of working out and measuring, because as you can see it's not center. I'll see if I can line it up here to show you guys. There we go. So there's the center of the piston, there's the center of the bolt, and there's where the electrode is. So the electrode's sitting off a wee bit. It's due to these 2 bolts. It had to be designed to get it, but it's good. There's nothing wrong with it. But the center of the piston pushes up and makes a wee bit off here, due to these 2 bolts. And I'm going to, before we go on to the transformer, I'm just going to flatten it here again now, or collapse it down. There we go. So as you can see, the guard stops your fingers from getting in. If your finger hit here, it wouldn't do no harm, because your finger would slide off. This comes down past. Can't nip you because there's a wee gap there, you know. There. Doesn't nip you, but as you can see there's the barrier. There's the other barrier through the guard, and there's the 2 bolts holding the brass block in tight all together. So when the force pushes up, this brass block wants to come this way anyway, because the 2 bolts are at this side. If that makes sense. Mechanical motion. And we're going to now move on. Oh yeah, just talk about this 2 seconds. I don't think I talked about this. This here's I think I better must this out. This is routed using the wood router. This nice radius. It's 10mm radius. But first of all, it is, you will see in the pictures that I square it up as square as possible first. So these 3 plates is welded together and sanded 90 degrees off each other. So this face is perpendicular to this face without the radius. Then I wood router the whole thing without this plate on it, obviously. This is welded on after. I wood router the whole thing right round the back up to there, and then it is hand sanded and wet and dried, done in final stages to get a nice smooth surface. Then it is anodized. This guard was built in a day. It's welded down here with a TIG welder. It's stainless underneath and it's powder coated. These holes is all hand bored. And it is now time to move on to the transformer. Okay, so this is the transformer that I have designed and built. It is customly built and designed using mathematical equations. We will go through them quickly in a wee minute. Not much detail, but just an example of how it was designed. The transformer is designed using E&A, or it is built using the E&A laminate. So you can see here that there's the E. Oh, you can't see it because of this secondary winding or primary winding on the insulator, the tape. But there's the E running up here, and there's the I. And all these E and I laminates are crisscrossed the whole way down. So you can see here, there's one going this direction, and the other one goes the other direction. And that finishes here. So there's no welding to this transformer at all. It's unlike the microwave transformers. It's more efficient. Now less eddy current losses. The clamping bolts go through these holes. So basically these plates, let me see if I open one up. There's the eye, and that's basically what I've purchased. Them two holes are on the outside and this is the inside, so this is where the E meets here. The E meets this face tight, a really tight butt joint. Really tight. The tighter the better, less losses. And I'm going to show you the E now. I go back into the assembly. And the E is here. So this is the E laminate. So this is the E. This is the biggest size you get in the single phase. I think it's EI86 or no, sorry, EI96. And basically we're looking with a transformer with the biggest AI, a biggest area on this phase here. So we're going to talk about that in more detail within the design. We'll go back into assembly now just to show you the breakdown of a transformer. So the transformer has few components in it, but this secondary winding is just one turn, or you could say it's half a turn, and it is made out of. I've maximized the amount of window usage I've used within the transformer. So there's two holes here, and I will show you now. And I'm just going to explode this up here. I'll explode it and I'll show you what I'm talking about. So I've maximized the transformer. I've used every bit of this window. I've designed the transformer by using all the window area within the E&I laminate, the core itself. So this bobbin here is custom made. Two coils are shown in the copper color. They indicate the primary at the top and the secondary coil at the bottom. And an alternating current flowing in the primary coil will cause an alternating flux in the core here, and which in turn couples with the secondary coil, inducing an alternating voltage in it. If this alternating voltage is applied to a load, then an alternating current will result. The ratio of turns between the primary and secondary is balanced, minus losses to the voltage on the primary and the secondary coil. The number of turns per volt is a function of the cross-sectional area of the magnetic circuit. So that's here, this face on here. I will break it down in a wee minute and show you more detail. Eddy current losses are constant, and the fraction of the primary current that is due to the cause of it known as the magnetizing current. The resistive losses in the windings due to the current flowing is generally known as the copper loss, and is proportionate to the percentage of the full load that the device is run at. We want to keep this minimum on the cables rolling to the clamp, so the bigger the cables that go into the clamp, the better. The laminations are sprayed with lacquer for insulation purposes and reduces eddy currents. So these is all coated in like a lacquer. The bobbins these days are mainly injection molded in plastic, but larger ones are often difficult to find and aren't manufactured at all. I made my own bobbin to suit a stack of 133mm long. Okay, so the exploded view here shows mainly the bobbin, primary winding, insulation tape, barrier between the primary winding and the secondary winding, and the bobbin was custom made using two bobbins that approximately 80mm long, which had to be cut because 80mm is the maximum you can buy. So I made a custom bobbin for the E&I, a stack of 133mm. So 133 mils from this face to this face on the inside, The primary winding name is wound round it. 131 turns using 1.4 double enamel wire, special wire. I will talk about that in more detail when I'm showing the calculations. Double coated. So 131 turns, and these 131 turns had to be so tight round the bobbin, like I'm talking tight here in right angles, because you had to reduce any wastage, any losses. You know, you wanted to maximize the much space you're using in this window as possible. So I was looking to use little, very little, because my secondary winding needed to be quite heavy for the high current. And okay, so rather than people that strip microwave transformers are running a couple of turns down using 16mm squared cable or something, this here I think needed to be 200mm squared or something for the calculations I've worked out, and I think I've got it up around there. Was it 200mm squared cable required for the high current? But because it's a spot welder, it didn't need it. It's only been pulsed, so I think I got it down to 100. I'm not actually sure. We need to look at it on the calculations in more detail. But here we go. So the bobbin is, the primary winding is round the bobbin as tight as possible to reduce any wastage off this window winding or this window area. The primary winding then also has a protective tape around it. It also acts as a barrier between the primary and the secondary winding. It is a special tape that is used for transformers, like a paper tape. It is sticky on one side and like papery on the other side. Papery plastic, sort of. So this bobbin goes on, slides on to the core. Now you don't slide it on because the stack is actually bolted around the core. It's not like it's not like a microwave transformer where you just slide it on. The core is crisscrossed the whole way on and bolted on a stack with on this bobbin. And this secondary winding then is slid in. I think the secondary winding is made up of 20 pieces of copper strip at 40mm wide. I think it's 40mm wide. It's the width of this E&I, roughly 40 on it as far as I mind. It is 4mm wide. That's as maximum as I could fit in, and the bigger the better, as it's high current. So 4mm, I think there's 20 strips in there at 0.2mm thick, and so it gives it a good thick cable. Like it's. We'll look at the calculations in a wee minute, and we will compare it with round cable. But if you were to put round cable in there, it wouldn't have been very heavy, because this is wound different from transformer winding. Transformers winded to one side. This is winded over the top of each other, so it's just done a different way. But they're still passing the core, round the core. These two plates at the side is barriers to keep the secondary winding from touching the core itself. It's like a papery, plasticky material, same as the core sort of, the bobbin sort of. I'm gonna just collapse it to be show. So there's the secondary. There's the paper insulator barrier between the primary and the secondary. There's the bobbin, and there's the insulator plates to protect the secondary from air from out against the core. As you can see there, the bobbin protects the top and bottom too, and the secondary winding slides straight on, and I bored holes in the end of it to allow M8 bolts to attach the high current cables. So we're going to do the calculations now. Here we have the design of the transformer. It is made on assumptions. So the first thing I done was find out the center limb area required, and this was done using frequency and Jerningham formulas. So it was worked out to be 4,256 millimeters squared, and turns per volt was worked out to be 0.57. I'm not going to go into it in too much detail because
it would take too long. Primary current was worked out to be was done not at maximum load, maximum VA. It was general assumption of 3000 VA, divided by 230 volts times efficiency was about 14 amps on the primary winding. Required number of primary turns, so turns per volt times the primary side voltage equaled 131 turns approximately. So I wound the transformer to round that. I've 131 of using 1.4 millimeter diameter dual coated wire, proper winding wire. I will show you at the end of the demonstration. The required size of the primary conductor. So here, yeah, I jumped the gun there. So that there is 1.4 there. This is done using the primary, or found out using the primary current, the copper current density. The secondary current is obviously the primary current times the turns ratio. So it worked out to be 1800 amps. Not at full load, obviously, because an assumption that was it's made an assumption. So maximum current could be over 2300 amps because 13 amp doesn't fuse doesn't pop at 13 amps. It will go right on up to 20 amps or more. So this welder might be suited to a 16 amp plug too. So the required size of a secondary conductor is the area of a secondary conductor, secondary current divided by copper current density. So this is the secondary current I worked out divided by 8.6 amps millimeter and equals 205 millimeters squared. So that's obviously very big. So that's for like continuous current, which a spot welder is not doing. It's pulsing or spot weld, so a matter of seconds. So the cross section of the area of within copper cables with 205 millimeters squared is massive, so it would never fit through the window winding. So it's far too big. So this is why I designed the secondary winding to be flat, to use all the window area, rather than designing it like a microwave transformer, the way the windings sit on top of each other. I set them, wrapped them around each other. So I used the most winding window area possible. So the width cross section there is 205 millimeters. So this is what I require, but this is all I could get. So cross section there is 205 millimeters squared. Secondary winding height. So this is the maximum height of them E&I. So that's 5.125 millimeters height. That's really more than I could give. Like so. The secondary winding is preset to have a space of 2.5 millimeters at either side of the bobbin. The bobbin's internal height is 45 millimeters shading height. Okay, so I left it at 40 for a wee bit of give. The maximum width of a secondary winding can consume is 4 millimeters, so I couldn't make the 5.125. 4 millimeters is maximum I could give, so could fit, because you needed the tape, and you needed the tape in the primary winding. You know, otherwise the whole thing would be useless. It wouldn't work. So I've says here a reduced size of 4 millimeter wide should be fine, as the current will never be continuous. Hence the current is never constant due to the spotting action. So the required number of secondary turns is turns per volt times the secondary voltage. And here we go. So the core area times the tongue width equals stack height. This equal to 133 millimeters stack. So this is all made of assumptions at the start, and then we work this out now. At a stack height of 133 millimeters, this requires 266 laminates, as there are 0.5 millimeters thick. So obviously when they're clamped on this, they will make up 133 millimeters approximately. The primary winding the primary winding side length is the perimeter around the bobbin. So we know what the bobbin is The tongue width is the standard size of the E&I laminate, which is 32 millimeters. So there's a top and bottom obviously, and then there's the two custom sizes that I made, 133 at both sides, equals 330 millimeters approximately. So lat times 1 turn of the primary, so lat times 131 plus 20 millimeters spare. So I added 20 millimeters spare just for curiosity, just in case. And that equal to 46 meters. So I required 46 meters from my primary winding. 1 turn was equal 350 millimeters, and that's give or take a wee bit extra. 46 meters. I think I ordered a lot more. I think I ordered 60 or 70, and I have a lot left over. So the perimeter around the bobbin is seen in appendix. We'll not look at that. And high current mount tab 1. What's this about? Okay, that's the secondary. This is important. So this is the the secondary current. So 1 times the width. Obviously, because it's not going around full turn, it's meeting halfway, finishing halfway. You could say it's halfway. It's in between halfway and full turn. Then 2 times the length, which is 133, equals a piece of copper bar, 398mm long, at 4mm thick, by 40mm wide. But the problem is there, it's a bit hard to bend it around the core, around them angles to make it fit in. So I've used multiple thin sheets of copper at 0.2mm thick times 20, and that gives you 4mm. So it worked out very well, and I think I don't know how much I ordered. I ordered a lot of that stuff too, and it was hard to get, hard to source. So alright, there's the electronics. We may as well give a wee brief talk about this too when we're at it. Okay, so here we go. This is the income supply. This is a power supply for the transformer. And let me see if I zoom in a wee bit here. This is the power supply for the transformer here, and this is the relay controls the main transformer. This is a pulse timer, off on clock timer. So you can, that's the one that can be configured to pulse. This off delay is the signal back. So this pink signal comes from the clamp. This is the signal back. This holds the transformer from starting for milliseconds. This is the stat that controls the two fans. You can see here the reverse polarity, negatives going on the opposite ends of them. So one fan's going one way and the other fan's going the other way. This stat goes into the core. This is the digital stat run off the power supply. Right, we're going to move across now to the clamp. So the clamp then has the valve, a two-way solenoid, pneumatic piston. It has the off-on duration clock timer. When that latches after a second, the signal is sent down through, where is it now? This pink wire here. This is the signal sent, 12 volts, and passes under here, and this pink wire, and holds an off delay timer, holds the transformer from start kicking in. This special timer that can be set to pulse. And this is the high current cables coming up to the clamp. They're denoted here by these dotted lines. This here is the main switch. So when you push this switch, this clock timer latches, and this sends a signal around to here, latches this. And this timer is latched, and the pneumatic valve is engaged, and the pneumatic piston goes out. As I say, the signal comes down here. The item is earthed, and the subject. That's really it. I'll see what's right here. This is the report I made for it a long time ago. There's a wee explanation there if you want to pause and read. The SY7 core cables is 1mm squared cables. This divide here is the SY cable. So this basically is the high current cables here passing through these two purple lines. and I'll zoom in again a wee bit closer. There we go there. There's the two high current cables coming from the transformer. So this is a transformer that I built. This is a live and neutral. Neutral is always straight on. Live is controlled by the relay. This relay is controlled by the clock timer. And it doesn't start until this delay time is finished. And the signal is sent from the clamp to that. So the signal from the clamp starts that and sends a signal to this. This signal is passed to this relay. This relay starts the main transformer, and these fans start when this probe here, and where J is subjected to heat. Okay, so we're going to move on down, see what's down here. There's a lot to this project, and I've done a lot for it. Okay, so there's current spot welder, really heavy and bulky, big transformer, and the big arms, I'm sure they're 200 mil squared. Mine's is 195, so it could be quite a bit of copper losses in mines, but it works, and it's a prototype project, but it works. So this is core design. I done this design here, shell type. And let me see what's down here. That's just me talking about the magnetic field. Data gathered, so I done a wee bit of data gathering about them heavy spot welders. Copper selection, that's just different kinds of cables. So 95 millimeters squared, and then there's 70 mil squared. 70 is what I use first. Clamping forces is well worked out from the pistons here, the pneumatic piston, what was required. What newton of force. So this is E and I selected the biggest one possible. Then I've extruded it to 133 mil long. Gantt chart table. I'm hoping to see interesting things down here. Okay, so there we go. So that's just what we seen a wee while ago. We're nearly finished. We're nearly on to demonstrating the welder welding itself. Okay, so it's just drawings now and exploded views. You have seen all this in detail. This is just all the parts now. So this is the 6 mil plates, pneumatic system. So this is all these parts is all drawn for. I'll speed it up a bit. All these parts is drawn and then put together in assembly. There's parts missing here. Alright, I'm going too fast. There's the nylon block, pneumatic piston, nipple, hex nipple, push fitting, meal stud. There's the enclosure. All the pieces is just hundreds. You could say there's hundreds across the whole project. Okay, look at this interesting part. This is the spacer between the two aluminium plates, between the hand, the spot welder. So that's actually cut out a grinder there, that part, and set on. As you can see there's the bit around the front. So that's the spacer that is welded in, and that's required to keep the device and pull on. There's the wee button switches that are made. That's the timers, timer control, PCB. That's the nylon insulator for the circuit boards, getting away from the handle. That's the guard that took a day to make. That's the glass fiber boards that cut, and the stainless washer that goes on top of it. That's the polycarbonate screens. That's the glass fiber protects the nylon block. That's the nuts. That's the coupling. That's all easy. So this is under the enclosure now. Just see through again. Looks better. No transformer this time. This is all parts. This is loads and loads of parts. You could say hundreds. So if we keep moving down here, this is the brackets for the enclosure, for the cover to the enclosure. And this is the switch. So all these needed to be drawn up here. These switches basically drawn up to make the project more complex. This is the brackets for the enclosure on the clamp design itself. So there was 4 of these. This is the wee board. So this is just drawn up to make sure everything fitted nice and neatly. It's a gland, cable gland for the SY control cable. That's the outer fans, grommets for the high current cables, the feet for the transformer enclosure itself, and the handle. This handle's made out of a piece of tube with two other tubes, and it's a plate welded on the end. They're also sanded and polished in the mirror. A lot of work on this project. This is the shafts to control the switch, and with 3mm washers. They're not washers, I had to actually make them. I think they're 4mm bored out to 3. 3mm washers too small, they'd be welding there, I think. A wee bit fittery. This is the polycarbonate window for the PCB enclosure. There's two of them on the enclosure itself, the transformer, and there's one of them on the transformer clamp. And this is the stat button controls. There's just loads of parts. I'll try and go faster here to move on. That's a transformer. This is all different parts of the transformer, roughly drawn out to get an idea of the usage of the window. They use as much, maximize the, leave no gaps. And I think that's it. That's the bobbin I made. So this bobbin was glued together in the middle using two other bobbins. The pictures at the end will show all this. Transformer power and efficiency, so it's 3 kVA maximum, roughly. It's standard results, okay. This is the drawing in detail, so if you want to look at it in detail. That's a handheld clamp wiring diagram, and that's the transformer enclosure wiring diagram. It's a bit more complex, but it's nothing complicated. This transformer is the one that was made here, and there's the high current cables. It's showing 1/3 of the winding here, but really it's sort of half. This ground runs up the shielded cable to the clamp in here. All metal objects need grounded, and that's really it. This latching device works really well. So when you push this button, this really doesn't latch for 1 second until you find your position when this piston goes out. When you hold it for 1 second, this clock timer starts. The 12 volt comes down here and holds the timer on until it finishes cycle. I've went through that already, but I explained it a bit better there. That's it. That's everything. Right, we're going to move on now. Alright, here's the building of the... I don't actually have pictures of this at the end, but here you go. There's building the bobbin and the... winding the core itself really tight. So you can see here that I have winded it really tight. There's 133 turns there at the minute. The bobbins are glued together with an epoxy resin. They are clamped because it's so tight. Like I was putting these E&I strips on, these laminated strips on, and it was so tight, because I've used so much of the window area. That's it finished. It's lovely. It's really neat. It's lacquered. I lacquered it at the end to keep them from rusting. E&I strips they are lacquered, but I lacquered it again to make sure there was... So you can see here that there's no welds. They're just butted together tightly using these rods. We're nearly finished now. I keep saying that, but there's a lot of stuff in this project. There's a lot of pictures of me building it, folding the box up in one piece. There's me cutting the bit off the toe now of the car, and there's the bits cut off for the corner of the box. There's it tacked on, and that's going to be purged then. That's the inside of the box, wired. That's the box finished, and you can see it's lovely and shiny, and a lot of work put into it. That's the clamp design. Okay, so this is the clamp design itself. So that's me welding it. That's me bringing it up to a square edge. And that's me bringing the guard up to a square edge. This is the enclosure before it's all sanded down and polished. These blocks is handcrafted on a milling machine and tapped. Then, and they're not done CNC or nothing. And they're just done a wee milling machine. This is where how I left the handle before I put the wood router near it. Nice square edge to work off, perpendicular to this edge. So this is the device finished, anodized and sanded and anodized, and it's beautiful. There's no defects in it at all, and that's it they need round it still. I still never got round it. That's it, finished. And there's my references, because I done a wee bit of literature review in this project. I think that's it.
Hi everyone, welcome back. If you stuck it this long, you're doing well, but we don't have far to go now. Okay, so I've been talking about it since the very start about taking the covers off the actual enclosure and showing what's underneath, but I got distracted with the 3D models. But some of the components that are under this cover aren't in the 3D models, such as the relay for the transformer and the wires, pneumatic pipe, stuff like that. Well, obviously that's not under the cover, but it's not drawn up in solid marks or on the model. So what I have decided to do now is take the cover off, show the workings underneath, then do a demo of the spot welder welding. But before that, I want to do voltage readings of the two electrodes. They show the low voltage of 1.75 volts. Then I want to do a current or read the amps running through the two electrodes here at this point. Or I might read it at this point here, which is the same thing in the loop. So this is the secondary winding basically that I'm reading here, the current running through it using this clamp meter. This clamp meter is rated to 1000 amps but can handle more. It's only short pulse. So a matter of second. And after I do that, I am going to run through the manufacturing process using pictures. I'm going to talk about them in small detail, so the video isn't too long, running under 3 hours. I think it's 2.5 hours as it is. Before we do all that, I want to show. You may notice my hair is different since I started making this video. I shaved my beard and my hair off yesterday. Today's Monday and it's been 2 weeks. 2 weeks yesterday I started making this video, as I said. So it's been a while. I'm going to show these two pieces before I go any further. So this piece here is the piece that I have pushed over a tow bar in the car to make the corners for the box. So if you watch the model, you will see that you're left with 4 holes here. I haven't modelled this up in the model, I haven't made the actual corners and set them in because it's just too much work. So what I've done is I want to just show it here. So basically this is pushed over, as you can see there's a bit of greasing inside it, because I put grease over the tow bar, a 50mm ball really, and I pushed this over using a press and a ring, a 3-inch ring. So it's about a flat steel, there's no heat, and it's been specifically cut in triangles here, as you can see. See the wee slices? Them slices is crucial to get that ball nice and round. After I done that, I have, let's see, I'll get this wee marker. So then you're left with, you've got the right sort of radius or diameter you're looking for. I have cut a nice curve. You will see it the videos at the end, and I have cut that out. It's a wee bit bigger than that actually, it's about that size. I've cut that out and 4 pieces, and I've set it into the box after the box is folded up and polished it and sanded it, polished it. I've went through all different grades. I've never talked about this in the model. I've went through so many different grades of polishing. Let me see, I'm going to just get them here. I've went through all these different stages of polishing, from salsa to brown bar. I have no black left, I don't like the black. Black's coarse, and then I have green finishing. I have pink in there too for finishing. All them different stages to get this box up to this shape. Obviously that box could have been built in my style or anything, but because it was a prototype project, I wanted to make it unique. And I'm now going to take the covers off and show you underneath. Oh yeah, one other thing to show. This is a small cover that was cut out in the laser machine after I drew it, and fibre laser. So the cover, this is for a smaller transformer out of a microwave transformer. a transformer out of a microwave, which is no good because I've been testing it with these high cables and all. I'm all greased now, and it wasn't any good. So what I've done is I've designed a bigger cover. So this other cover came out here, another 100mm, and that's where you get this box. So I'm now going to do a walkthrough of underneath the cover, and then we will do a demonstration after do a wee short clip on voltages and currents. So I'm trying to get the camera as close as possible now for this. So we now have the temperature probe here disconnected, and we have the relay sitting out of its housing, and we have the primary winding disconnected, the live and the neutral wires here. So this cover is all designed to be complex to slide on. We're going to move this spot welder back a bit so it doesn't get marked. This here slides off now, like so. Down the cables, and I might just keep going yet a bit. So you can see that the transformer is lacquered. There's a wee bit of rust starting on it, right enough I can see. That's why I bought everything out of stainless, because it obviously doesn't rust. 316 marine grade or right. So now I'm going to keep going yet. I feel like I'm destroying something here when I'm doing it. No, I'm not. I'm alright. Okay, so I'm going to keep going a wee bit. So now, this is a really good video. I think it need this. So we're going to take the camera off. So this is the transformer that I've built. It's built out of loads of copper strips at 0.2mm thick. There's 20 of them adding up into 4mm. 2 high current cables and 95mm squared. So you can see there's a lot of copper in them. Over 13mm, 14mm thick. I think an ordinary spot welder arm is 20mm. One of them 500mm arms. So we have them bolted to here using 8mm screws, base stainless screws again. And this here is just to hold this relay, obviously. But it's the handiest way to take it off and on. You just clip it on and out. This really looks damaged, but it's not. It's if anybody ever pulls the cover off, I really usually think you destroyed it, but this just slides straight back in. This bit of plastic nylon board here protects all the other extra components, such as a switch when I put the cover back in, from hitting the secondary winding, from shorting out against it. This winding is basically comes down through the core here and back up through. You can see here I have the transformer, the E&I laminates squashed together with a 5mm bolt threaded bar. Now if you look closely at this transformer, you can see a slight radius here. That's because there's that much tension squeezed here. Really, I should probably have a plate against this, but it's okay, it works. And then nylon blocks, you say, is one side's full of epoxy. They're actually a bolt counterboard in, and it is. I'll try not to chuck the closure off the table. I'm going to set her up on our side here. So here you have the bolt. Well, that's going through the nylon block to hold it to the body. Them two bolts do not touch each other. The two of them is offset and counterboard to act as an insulator for the primary winding. This is the temperature probe. I slid out of the core before I took the cover off. I'm going to now flip this over the body without marking it. I'm going to sit this in here and move this device back a bit. We don't want to scratch anything, you know, because I'm a bit of a, everything is to be precise to me. So there's nothing on here to mark the cover. I hope not anyway. I might just set something else on it. So we'll set this underneath the cover too at the same time, and we'll chuck this over to let you see the inside of it. Okay, we'll go around this side. See what's dark in here right enough. We'll chuck this over the body too to match it. Yeah, we'll chuck this over to match it. Okay, so here we are. This is the inside. You can see there's a lot of wires and cables running everywhere. So these are the two high current cables that I have slid out of the two grommets. This is the 7-core SY cable, control cable. There's probably so many loops there not used, and all the wires is cut off, it's not used. Usually I would loop them up, but it was finalised that these extra 3 wires was not needed in this cable. And if they ever were needed again, I've just replaced the cable. And here, I'm not going to walk through the wiring in detail because it's too hard to see, there's too much going on. I talked about it in the videos about, so this stat controls the fans, this digital stat controls the fans. Okay, so I'm going to give it a wee quick talkery. So when I push the button here, the transformer, and when I push the button here, this clock cycle timer, countdown timer, shoots a pneumatic cylinder out for say 5 seconds. Within them 5 seconds, the first second, 12 volts is sent down this SY cable here into this, and into this in here you have a delay timer, and this delay timer holds this CN here and under, the one that you can control. This holds this pulse timer from stopping and starting, and this pulse timer then controls this relay, which then controls this live going to the primary winding of the transformer. This blue is obviously neutral, and that there decides just a 12 volt power supply. That's just a switch. The connections are soldered onto the switch because spades, those crimping spades, is too big and bulky, so they would hit the transformer if they were in there. You can see here the box is purged the whole way down, so this is welded on the other side. The reason that is done again is they allow me to polish the box the way it is polished. And if we look, I'm going to show you one of the corners and inside without marking the box. So I'll turn the light on, hold on, I'll turn the light on. Hopefully it's better with the light on. There we go, there's a wee bit of difference. So in here in the corner and under, I'm going to try, I might just zoom in here. In here and under you can see the weld where the wee bit was set into the box. In here, let me see if I can point it. Over here, there's that much going on in here now, you can't see it no more, but the box is fully purged. That's really it. So I'm going to put the cover on now and show you the device working in detail. There we go. Okay, so now we're going to check the voltages on the secondary winding, or between the electrodes, with the air supply disconnected here on the right. I've disconnected the air from a pneumatic cylinder, so we don't want the pneumatic cylinder to shoot out when we are checking the voltages, because we want the circuit to be open, so open circuit voltage. So here we go, on to the 2 electrodes. We have 0 the multimeter, and away we go. 1.782 volts. So it's very low voltage. So even if I was to touch here, it wouldn't penetrate the skin or break the barrier, the resistance of the skin. We are now going to put the air supply on the device and check the secondary current. So what I've done now, I've connected the air supply back up to the pneumatic cylinder. I'm going to place this bit of copper in between the electrodes to try and keep them clean. And the clamp meter is around the secondary winding near the transformer, which makes no difference if I put it there or the electrodes. And I will put this bit of copper in and push the trigger and see what current reads on the device. So there's 1700 amps. Really high. You can see the cables under load. You can see them move. So we are now going to test it on a bit of metal, demonstrate it working. So what I'm going to do now is I'm going to sample welding this handle
which is quite weak on this actual pot itself, and you will see the current. You'll see it glowing red and clamping. So here we go. I'll try and get it down the trigger. You see the smoke rising there. And there's the wee weld on the pot itself. The handle was getting weak on this pan. So I'm going to demonstrate it this side. Now I'm going to bring it up close so you can see it welding. Here you see. There. Works really well. There's 2 welds on the handle to match sort of the size of the weld that's on it, but really good. Okay, so I'm going to show this spot welder now working with no air in it. Again, I'm going to bring it forward. I'm going to show the spot welder latching and then activating the transformer housing. So you will see this latching. So the piston's not going to shut out because there's no air. I don't want the electrodes to touch. So here we go. And there we go. So basically I could set this up to pulse, but I need to increase the clamp time here first. I might do it just to show you. So I have set the settings now up to pulse. So when I hold this, piston will shoot out. This will stay on. Transformer pulses, off, pulse, off. Okay, so now we're going to sample clamping welding these 2 pieces of stainless together. They're 0.9mm thick. So here we go. The spot welder is set up to pulse. So we're going to start here at this end. You can see it glow on there. Down here. Next one. Need to watch the fingers from the clamp. Here. And finally, it's hot. It's really hot. There. So there we go. There's the 5 spots. It's really hot. I'm going to chuck it down here. And that's the spot welder. I hope you've enjoyed it. It is different compared to other spot welders that have been done on this channel or YouTube even, and I never showed the exact place that the airline hooks onto, but there it is there. The core was at 13 degrees, it rose to 16 degrees. But I like to keep welding to show you the fans coming on. I might do that, just hold on. I may as well just do that since I'm standing here anyway. I've spent enough time and everything else. So I'm going to keep welding. Oh, there's the core just coming on there now. The fan's just coming on for the core. At 17 degrees. One's sucking and one's blowing. If I get a wee bit of paper here. I don't have a bit of paper, but this might work. So that one's sucking. And this one's blowing. This won't stick. I also had a bit of paper, but I don't have a bit. I might just give this wee plate a couple of more welds to get a wee demonstration again. The clamping pliers. This is really hot. I'm going to have to put a pair of gloves on. Hold on. So you can hear the fans singing there now. Since the fans came on there, the core has dropped back down to 16. 16.4 degrees. It was at 17. I'm going to keep welding here to see the core temperature go up. Okay, so I'll try and get everything in the camera view. So I'm going to keep welding till you see the core temperature rise past 16. That's 16.1 now. So I would like to get everything in the camera here, so it's quite tricky. Okay, I was zoomed in there. So it's a 16 degrees now, so the fans is cooling it down because it's that cold today outside. So we're going to keep welding. So she's pulsing. I still have her setting up for pulsing. So I want to try and raise the core temperature up to say 18 degrees. Incredible, really good. Right, so we'll keep going down here. So remember that I'm holding the button for a second. I'm holding the button for 1 second. I want to get away from this enclosure because there's sparks coming off it here. There's sparks coming off it. I don't want to destroy the mirror. I know what let me see if I can get closer here. I know I keep using the same bit of metal here, but I demonstrated it in the saucepan a wee minute ago, but I'm trying to raise the core temperature. So the beeping noise is the wee beeper, just a wee speaker, sort of, wee buzzer. Yeah, it's hot now, I can't hold it any longer. So there you have all your spot welds. They're quite fine because the electrode is very shaped to be fine, you know, the end of it. There you go. Oh, melt that. I'll get down the ground. Okay, so that's it. I hope you enjoyed it. I'm going to talk through some of the photos making it. So yeah, the core temperature now is at 19-20 degrees. It should start dropping soon again because the air is not cool out here today. 19.7, 19.8. It'll start dropping again now soon. So it'll go right down to 13 degrees and the fans will cut out, or maybe it might go, I can set it up to go below 13 degrees or room temperature. Keep on going below it if possible, if I can, and depending on what temperatures it is outside, the fans might keep on going, so you don't want the temperature to be set too low. Okay, so I hope you enjoyed the video, as I say, and it was a long video. I've been meaning to do it for a long time. Okay, here's the wee brackets. They're all cut using the laser machine for the clamp and enclosure. This is the handheld clamp and the early design. Welding the pieces together for the wee small enclosure. This is the handle and the clamp all in early design. This is it being welded, started to be welded before being sanded. This is the enclosure fully welded. The end being filed with square edges. This is the wee enclosure polished up after it was sanded. This is the clamp and early design again. Started to polish the wee enclosure. The this is the clamp being wired with the setting the mirrored polish enclosure on the clamp itself to check it fits. This is it in closer view, showing the wires running to the digital timer that controls a pneumatic valve. This is me setting the mirror polish enclosure on the clamp. This is me making the electrode holders, the brass blocks. They're both of them the exact same size, but the holes is bored in different places. Using a milling machine. The big holes for the electrodes is 10mm, and the mount holes is M6. Here we are boring the holes, the M6 holes, well they're 5mm and then M6 tapped. The tap is put into the milling machine to square it up against the block to make sure it is true. Nice neat cut. These is the wee brackets for the enclosure on the clamp. Tapping them too. These is the blocks finished, just need polished. They are tapped for the electrodes and the cables themselves. On the mount holes, this is the copper board that divides like a heat barrier plates. There's 2 of them on the nylon block. This is the electrode placed into the brass block that holds it. And that's my dog, Azimo, he is the man. This is the block polished, I think. Half polished. This is the wee brackets on the clamp design that will hold the enclosure. Wires for the controls on the switch. Pneumatic cylinder in position. This is the SY cable run from the panel enclosure. This is the top piece of the arm that holds the electrode, the top electrode in the brass block. It is welded on with TIG, the TIG welder. You'll see the next photo here. So this is it welded on. This arm then was polished into mirror, sanded, a few different stages. The wee support at the top holds the brass block nice and square and tight, so it doesn't depend just on the M6 bolts. Here we start making the nylon block on the milling machine. We started cutting around it, I think. As far as I mind, this a couple of years ago now since I started it. I think that might have been one of the first parts I was making. Yeah, it's countersinking or counterbore in the center of it. Tapping the M6 holes or boring the M6 holes. This is me squaring the block up. Nylon block. So the nylon blocks and insulators is it finished. This is the piston and the bolt that nylon block will be placed onto. This is all the wee pieces again that were used for the closure and the clamp. This is the block screwed onto the piston for the first time, nylon block. So this block is subjected to the force from the piston when the electrodes is shut. Next photo is the washers where it goes right down the clamp to keep the clamp from pulling on when you're welding the 2 bits of plate together. This is it being squeezed together, then welded with a TIG welder. So I started welding it there now when this washer was in, this spacer. That's it, welded, the clamp. So it's just a matter of sanding it now. Here we have started flattening the welds using a file, I think it was a file. Or a grinder, being careful. Ready for sanding nearly, we're nearly close to the square edges. This is the top base plate for the pneumatic cylinder, welded. This is inside the handle, welded. It needs file too, so I used a carbide bar to do that. And a drill. This is it nearly almost started to be grinded. Files. So this needs sanded in there too. nice and neat, so I think I used sandpaper to get in there, or a Dremel. Don't have all the pictures for building this. This is it nearly finished. So you can see the nice curvature at the back for the on the palm of the hand. That's the nice gap in the middle. It's a nice fill to it when you the clamps in your hand. This is the clamp nearly finished. What needs routed. Nice curved edges on it now. So the square edge is somewhere for the router to run against. So it needs to be so square before I cut the round edges on it. I think there's a photo here with the wood router. That's the wood router there. Next photo shows a wood router. There you go. Leaves a nice curve. I think it's 10mm radius. Right round the handle. So that's his first cut. You can see the bearing there running along, leaving it shiny in the middle. That's why you wanted the square edge first. This is the handle nearly rounded, so it's a matter of a stage of sanding the whole body in. It's sanded and wet and dried, I think. Or it's just cut with a router even. So the next upcoming photos shows the handheld clamp being sanded using water and emery cloth or emery paper. 400 grit, I think. A dual action sander, 2-inch dual action sander first. This is it more or less finished. You'd think it was done in a CNC machine, but I have spent a lot of time on it. That's the size of the clamp compared to a Coke bottle. This is me using wet and dry paper now to rub out any fine scratches before it's anodized. This is me just testing, polished the mirror to see if it looked nice, and it actually did, but I decided to go with anodized to protect it. So I made a box and sent it away to England and got it anodized, as I didn't want to buy the kit. It was too expensive to do one wee piece. This is it anodized and me starting to build it together. This is me making the guard for the clamp. Took one day to start with me, what you see there, to the yellow guard, all the holes. 8 hours, or 9. I say that, but it probably took a full day. It's probably powder coating it at night time. So this is me starting to fabricate it using stainless steel. The back plate is thicker than the sides, for reason being for the guide, for the nylon block. This is it coming together with one side left to put on. It is basically a fuse down the end there of the TIG welder. This is me sanding and grinding it to make sure it's all nice and square before I start boring holes in it. Holes is for to reduce the weight, but also for looks. So this is it starting to be grinded too. This is the holes where I just bored on with a template using paper. So I just set it up in Microsoft Word or something. Or it might have been SolidWorks, and then I just printed it out and set it on top of it. The paper's lying on the bench there somewhere. There it is there. So this is me boring holes out to 6mm. I think they were 6mm or maybe... Either yeah, they're 6mm. Wouldn't be any bigger than that. So you can see what's going on behind the guard too, you see. Maybe they're a wee bit bigger than 6mm actually, 6.5 or 7. So this guard is powder coated at home. In the oven there now. House oven. Powder was first applied to it with static, and let's paint it yellow for obvious reasons. Keep putting your fingers anywhere near it when the device is in operation. This is it completely finished the day after. this is the clamp completely finished, polished up. It powered up. It's only powered up when you push the button, mind you. So this is the enclosure manufacturer coming up now. Here we go. So this is drew out in the laser machine as a model first, and then I flattened it and cut it out in the laser machine. This is me starting to fold it. It was folded hundreds of times in hundreds of positions. Then you're left with these 4 round holes at the corners with nothing to put in them. I started to pull it together because the folder ends sort of useless trying to get on there. I had to pull it together a bit. Work it together. The tooling can't get in because the box is so complex and tight. So then you're left with the 4 holes. So this is the design that came up for pushing metal over a toolbar of a car, and then cutting the corners out and welding them in, tacking them in first, filing them nice and neat and making sure they fit in perfect. Then I have purged the box, pushed all the oxygen out of the box and filled it with argon. The box was first taped. The base had to be finished to put on the bottom of the box first before I could start welding it. There's it ready for welding, a nice neat gaps, and all sanded. So it was welded over the top of this now. Ready for welding here. So I started working at the base plate and finished it before I went any further. Blocked off all the holes by putting the feet on the base plate and plates at the side to keep the enclosure in place. It's there. So that was flattened and sanded too, that weld. Me still working at the base. This is the base finished and ready to... There's a transformer hole, so 4 in the middle. Sanded, ready, all ready. So the base then is placed back on and the enclosure cover. There's a trap door, sort of a trap to keep the argon in, push the oxygen out. So this is when I start welding the box in, where I make the handle first. That box is actually brushed stainless at the minute, and I have to remove all the grain using different grades of sandpaper before I polish it into mirror. A lot of work. I should have got mirror polished first, and then I could have tweeted it and end up in. This is the handle, making the wee round bits at the other end of the handle. This is the mounting point for the handle. I think it's M6, nut inside the washer. Some people comment it looks like a toaster at this point, but it's different. A vintage toaster with no hole to put the bread in. Okay, so this is the digital circuit that controls the transformer. You can set it up to pulse, because basically it's just a clock cycle timer. This is me lining up, this is a footery bit, lining up the wee bolts. 3mm bolts or 4mm bolts was it? They hold the nylon extrude. This is what isolates the board away from the cover itself. This all had to be done before the box was sanded to polish in the mirror. These was a lot of work here. These wee guides for the pins for the buttons. 3mm tube. Very fine work. This is it all in position, the nuts on the board. This is the outside of the box with the wee buttons. This is a delay timer that holds the transformer from starting until the clamp is out. This is a purge. The weld is grey, but they're cleaning inside, so the way purging goes. 4 corners needs welded. The box has been taped up and 1 corner has been welded at a time, making sure all oxygen is pushed out of the box. Don't know what I had that plate for, to block off a hole maybe. This is the purge line running in. This is a purge and inside, nice and neat. So it's welded right through. There's no gap whatsoever. This is it finished, purged. That's a much stronger job too. This is the handle finished to welded. This is all sanded then and sanded down and polished into burr too. For looks, as it's a prototype. This is it squaring up the edge in the handle with a die grinder, bench grinder. This is the outside, needing prepped, sanded, filed, all the grain took out of it, all the marks and sanding marks took out before it could even be polished. This is the handle, sanded, ready for polishing, using salsa weld first. This is a coarse polishing weld with black compound. This is the box, been starting to be grinded or flattened using sanding this, or no, sorry, sanding this for the grinder. Flat discs, making sure I don't put no, there it is there. So that's sanding, a grinder dust on that. With like a sand, I forget what you call them now. You might see them in the photos here, they're a flat disc with rubber back on the grinder. So this is it ready for DA sanding, take out all the marks. As you can see there was a lot of work on it, I got it easier just painting it at this stage. So here we are still have to take out all these marks. There's weld down, 4 welds down one side, or each side. This is it being sanded with dual action, so I have to go emery paper in here now, take out all the rest of the marks. This is coming close to polishing now, but I remembered that I forgot to bore holes for the digital stat on top of the box for the cooling. This was forgot about during the time of the laser machine. Here, so I made a template instead and put the template over the box and cut the holes myself, not using the laser machine. So that's finished, nice and square because I used the template that I made. So this has to be sanded again around this area and filed them in the nice square edges. All the me extrudes had to be put on and wee tubes for the buttons. That's me starting to polish it with salsa weld, black compound. Coarse, so that's polishing up to about 600 degrees, right round. It's like burnishing. That's it coming close to the mirror. This is it, more or less finished I think. Which was a lot of work to get it into that. I think there's still full of polish yet there. You can see the engine and engines beside it, the reflection in it. You might be able to see the reflection of the roof. There's the reflection of the bench in it. I think there's pictures of it outside. There's me in it. You'll see pictures now coming up of the roof. Insulation on the roof of the yard. So the next picture coming up is outside images, showing sky, trees, branches reflected in it. A lot of work involved in this project. There's the trees. Looks like a Christmas card. This is inside the device being wired, starting to be wired. The epoxy around the wee glass, holding the polycarbonate glass on for the boards, 2 of them. Could have used clear, but I only have black at the time. Never see it on there, so this is me still wiring it. Circuit board again for the pulse timer for the transformer. SY cable gets struck back and wired to the enclosure relay that controls the transformer that is being controlled by the pulse timer. This is the SY cable all struck and wire income supply been wired and nice and neatly wired around to let room for the transformer to sit in the hole. This is the living room floor. So this needs to be wired now, so the wires is away from the middle of the closure, so the transformer can fit in. This is it wired together in two enclosures. And the switch is in the closure for the clamp there. So there's a good lot of wires in there. There's at this time there was, what do you call it? The clamps for the switch, but they were no good, so they were soldered on instead, the wires. Two insulating blocks for the primary end of the transformer, filled with epoxy around the caps, so two screws are no continuity between them on each block. This is it all wired for the cover ready to go on. The transformer was painted red at the start to keep it from rusting, but then I removed it and painted it with clear lacquer instead. Just be thinners. This is me setting the cover on the wee tabs that are tapped, the 5mm. This is compact, it's all put together tight, the wirings all nicely neatly laid out, as you see me taking it apart there earlier on. So this is a transformer manufacturer now coming up. So this is the big length of secondary winding. Well, it's not, it's lightning cable for side of a building. It's 40mm wide. This is the two bobbins that were only 80mm length, so I needed 133mm length. So I cut them and the ends off them, and I joined them together. One of them was cut tight, and the other one was cut different lengths. Obviously, they make 133mm on the inside. Just using the miter saw, bench saw. This is the primary winding, double coated wire. So there's two insulators on it, two protective coatings. It's 1.4mm diameter. It's worked out from my calculations. It's a, how many turns was it again? 100 and something. That black stuff's the seam epoxy. They stuck the polycarbonate clear screens onto the enclosures. This is me starting to wind it. They had to be winded nice and square. Otherwise there'll be no room for the secondary window, or the secondary winding in the window area of the E&I core. So this is it fully winded. Its laying had to be covered in tape, like a proper tape for winded transformers. So I have a lot of wire left over. Again. So this is a secondary winding in this next picture. All set together with cable ties. Roughly 400mm long each strip. Two holes bored in the end of them. So this is me wrapping the primary winding up to protect it, and to protect the secondary winding. That will sit around it nice and tight. This is me sampling, just seeing how the E&I stack up, but it obviously have to come off. They wrap the primary winding fully, so they all have to be slid out again. They're just basically crisscrossed. This is me clamping the secondary winding to get a distance off the, see what the thickness there. So it was 4mm thick. I just get an idea that to see if it would all go together, the E&I laminates crisscrossed. This is a glass fibre stuff that I have positioned over the tape to act as another barrier. That's very sharp, that stuff there. As you can see the way it's bent. So I taped the axle secondary winding right up too, right round. So this secondary winding wasn't pushed through like in a horseshoe action. It was the E&I laminates was stacked up, right? You'll see now in the photos coming up. It was built like this, because it needed to be clamped. You wouldn't be able to pull that out if you tried. So tight. I used all the winding window area as what the plan was. This is a transformer finished. I wish I never put the red paint on it, but didn't have clear lacquer at the time, so it took a brave lot of hours removing it all again. This is me clamping the ends on, eyelids, and putting shrink wrap over them with the lighter there to heat them. So you had to strip back a bit of the primary winding because don't forget it's covered, double coated with like an enamel. Final pictures, I hope everyone enjoyed. I'm sorry it took so long to cover everything, but there was a lot of work involved in this project. Please come back to see other interesting projects that I have built. I'm going to upload it in another couple of weeks. The world's largest aperture, it's as unique as this project, and it's really interesting. Please subscribe and like to see more. Thank you, bye bye.